In this video, I will be explaining in some detail on how to use the custom communication protocol that we have been developing in the past 2 to 3 years and how it works. So the custom protocol that we have developed is RoCo or RoCo for some people. So this was written by Arjen Zimmerman, and you can have a look at the repository if you already have access to the repository. So it's in EPFL Xplore and RoCo and in the RoCo repository. So there are multiple branches on this repository. The one that we will be using for the microcontroller and for the Jetson is the EL-BroCo with everything here in caps. So you can just go on this branch, and you can see here the code that was developed for this year. So it was developed as some kind of package that can be used on ROS. So it's actually a ROS package, but can also be imported onto a microcontroller project as it is cross-platform. So we have imported this library in our project, so you can see the previous videos on how to get started with the microcontroller side and how we've actually updated the library. So I will show you a bit how this library is used, about its structure for a bit, so you can have some deeper understanding. I won't go into too much detail as it won't be necessary to understand too much about the protocol either. So what you have to know is that in the RoCo protocol, first there are multiple folders here. So the most important ones that you will be using are the build.h inside of the include folder. You will have the canbus.cpp and also the protocol folder. Let's first go in the build.h folder. So these are some build options that you should use in order to have to build the library for the correct platform. So if we are on Linux, we want, for example, to use the CAN socket driver, whereas if we are on the microcontroller, we want to use the build with FDCAN option. So in this case, we are on the microcontroller, which is why I am uncommenting this line and commenting this line. It might be a good idea also to create a new build directive here. So I just did it for build for EL 2023 because we are working with for ERC 2023. But it is possible to just reuse this if it's fine with you. So this is for the build.h. Then there are some other functions, some other protocols, some other files here that you will need to modify if you want to add some new messages. So let's go first in the protocol in the canbus.cpp. So this CAN bus here will define the ID of each message. In this case here, I've defined, so we need to define in this file here the different packets that we want, as well as their IDs. So the IDs of each packet has to be different. Right now, the number of packets is limited to 64, but it is possible to add more packets, and I will show you how very soon. So the canbus.cpp here is a file that we have created because we are working with the CAN bus. But last year, for example, we were defining every message in the message bus, or not the message, but it was in the network bus function because we were using the UART protocol instead of the CAN bus. But this is really just a way to structure our code, but it's not like the name is not very important. So here we've defined everything in the CAN bus for the packets. Then we will have the protocol registers where you need to register the packet. In our case, we are working with protocol 23, so we need to register each packet inside of the protocol. And then we also have some other very important files. So the last important file is let me find it. It's inside of the protocol 23.h. So this is the one that we used for 2023, for ERC 2023. So in this protocol here, in this file protocol 23.h, you will find the definition of each packet that we use. So these, here you can see all of the packets. So you just need to define it, define the type of packet, as well as the name of the packet and what it contains. So when defining this, there are multiple things that you have to take into account. The most important one is the size of the packet. So right now, as we are using the CAN bus, and in more specifically the CAN FD bus or FD CAN bus, we are limited by one factor, which is the length of a packet. So the total payload of a packet, which is the number of data that we can send right now, is limited to 64 bytes of data. So this is a very important limit that you have to remember. And this is why for some of the packets, I had to calculate to compute the maximum number of bytes of a single packet. So let's talk a bit about the structure of a packet. A packet in RoCo is defined by multiple like fields. So the first one is the preamble. So the preamble is the first thing in a packet which is defined in the code of the protocol, and this preamble here will take 1 byte. Then we have the packet ID, which is basically the ID that we've defined in the canbus.cpp here. And this ID here will also take 1 byte. So we already have 2 bytes that are used just for the preamble and the packet ID. Then we will have an optional field here. So this ID field is equal to 2 bytes, and it is equal to the ID of the board that we are working with. So if you remember on the PCB, on the Orion PCB, we had a small dip switch. So let me show you this. So here we had a small dip switch here on which we could select the ID of our board. And this ID is optionally sent also in the packet. So for this year, it's actually not optionally sent, but you have to send it for the code on the Jetson to work. And in order to send it, you need to define your packet as an identifiable packet. Okay, so I will explain to you what these types of packets are very shortly. So there are 2 bytes for the ID, and then there are also at the end 2 bytes for the CRC. So the CRC is the cycle redundancy check, which is a number that we compute depending on the data that we are sending. And this number here can be used to check the integrity of the data. So we actually compute it on the microcontroller, we append it to the message, then we send it, and on the Jetson or on the receiver side, we will recompute the CRC and compare the CRC that we receive versus the CRC that we have actually computed. And if they are the same, then we say that the packet is reliable. So this is why I write the type here as a reliable identifiable packet. So reliable means that we are computing the CRC, and identifiable means that we are adding the ID of the packet, which is the ID corresponding to the board ID. So you should compute here, you should always try and compute the maximum number of bytes that you have in your packet, and be sure that it does not exceed 64 bytes. So here for the messages that I was not sure about, I computed the bytes by hand to be sure that it did not exceed 64 bytes. I will also show you some tips and tricks on how to not exceed 64 bytes that I had to use sometimes. So, but I will show you this later. First, let's talk about the type of packet here, the type of packet. So now if I just do control click to see where this is defined, you will see here in the protocol macro file where we define the types of packet. So you are free to add your own type. These are the types that we've defined this year. Just turn off the camera. So these are the types that we've defined this year. So we have a standard packet, which is simply structure with a packet name. And an important part here is that it is a packed structure. So packed means that we are compressing the data in such a way that there is no padding between the data. So let's say that we have 1 byte of data, and then we have 2 bytes of data. Then the packet will be 3 bytes of data if it is packed. If it was not packed, then the compiler might want to add an extra byte between the first byte and the 2 bytes of the second structure, of the second field of the data, because usually the compiler wants the data to be aligned on a certain number of address. So if we are using an STM32 microcontroller, the 32 means that we are using 32 bits as an alignment address, which is 4 bytes. So if we don't pack it, it might want to align our data on a 4 bytes, the 4 bytes alignment structure, which means that, for example, we could have 1 byte on the address 0, so 1 byte on 0, and then if we don't use the packed, we might have the 2 next bytes on address like 4 or 3. So 0, 1, 2, 3, and then we could have 2 bytes on address 4. So this would give us a total length. The total memory that we get would be from 0 to 5, because this one would be on address 4 and 5. And if we pack it, we'll have 1 byte on 0, and the next will be on the address 1, and the next on address 3, because everything is packed together. So we don't have extra padding between the two fields of our structure. So basically, in summary, the packed just compresses all of the data so that we have no space between the memory that describes our structure. So the structure is, as I've said, defined here, and this means that we have no padding between all of the different data structures here. So this is very important so that it can be cross-platform, and that the Jetson can, so that on the Jetson and other microcontrollers we can get back the data, because some microcontrollers might add different types of padding if we don't add this attribute here. Okay, so this is the standard packet, so there is nothing else other than the packet definition. So the packet definition is, of course, here the different structures. And now we can do a reliable packets. So the reliable packet here has an extra field, which is a 2-byte CRC. So this is the cycle redundancy check that I talked to you about before, and it will be placed here at the end of the packet. Then we can have an identifiable packet where we add an ID. So this is an ID field, which is also 2 bytes at the end of the packet. Then we have a reliable identifiable packet where we add both fields to the packet. And finally, we have some macros here, which I will show you in the code, which I use to actually compute the CRC for this packet, so that we can just add it we can compute it and add it to the packet by just calling this function. And there is also a macro here, which is used to compute the CRC from the packet, so that we can and compare it to the CRC of the packet, so that you can see if the thing that we are receiving is reliable or not. So I will show you these two macros in a more practical example. All right, so these are basically the things that you need to know. So I won't save it. So how do you actually use this in the code, and how can you add a new something new in the code? So let's walk a bit with the HHRS thread, maybe, so you can have an idea of how everything is working. So let's go into the loop function, I guess. Yeah, maybe this one is a bit too complex. So we'll go into the potentiometer thread for a more an easier to understand example. So what we do first is defining a packet. So I define it as static, And this is the packet that I defined here. So static is so that it is only available in this file. So this is the thread file for this sensor. And I define here my potentiometer packet as a pod packet. So this is just the way how I call it. So if you remember, the potentiometer packet here is defined in the protocol 23.h. In this case, we have it as a reliable identifiable packet, and the only field inside is 4 angles. So this packet here will contain um, the angles that are computed from the ADC of the sensor. So I just show you the board if you don't remember what it was. So file, open project, go inside of the hats, ADS, and this is the board that we are working with. So it's just an ADC, the ADS1115, which can read a voltage from 4 different channels and convert it to an angle inside of the code, which then sends the data through I2C, right? So I've already explained how this works in the dedicated video for this sensor. And so you don't really need to know more about this in this video. But what you need to know is, so we've defined here the packet as a reliable, identifiable packet with this single field here. So if we had to compute how big this packet is, we will have a preamble, which is 1 byte. Then we have the packet ID, which is 1 byte. So this is 2 bytes. We have the CRC, because it is a reliable packet, which is 2 bytes. So that gives 4 bytes. Then we will have the ID of the sender, because it's an identifiable packet. So this is also 2 bytes, which gives us 6 bytes. And finally, we have 4 floats. So each float is 4 bytes. So that gives us 16 bytes plus the 6 bytes that we've just calculated, which is 22 bytes. So this is enough. And this is not too big to send on the CAN bus. So this is the packet that we've defined. We can also define here a potentiometer data structure. So this is optional, and this is more as a way to add more functions to the packet. So let me explain a bit more. So potentiometer data here is defined in the data structures file. So this is not part of RoCo, but this is a local file that we're only using on the microcontroller and not on the Jetson. So it is defined on the same level as the threads, so in the include here. And you will have here the data structures. So data structures.h. So in this file, we just define like a different, just a way to print whatever we are working with. And also a way to convert this data here, this structure here, to the packet. So as I've said, it's not it's not compulsory. You could just create your packet and access its members directly, and it should work fine, and without going through this part here. So I will explain to you in more detail very, very shortly. But what is important here to know is if you plan on creating this so that we can have the toString function, then you need to understand the following part. So first, you need to define here the fields of this structure. So this is exactly the same as before. So we just, if you remember here, we had the 4 floats. Then I defined the toString function. So this is just a way so that we can print the data. So as I've said, this is not necessary to use this structure here, but an advantage is that you can add functions inside which can be used to print data. So this is what we use here. We have a toString function which takes a buffer. So the buffer is defined somewhere here. I don't know where. No, I'm stupid. It's just it's part of the function. So yeah, so the buffer is just an argument here, and then we just append to the buffer the following. So this is just a C-style printing, very easy. So we just print the different parts of our values, and we return the buffer. And then we also have the toArray function. So this one is used to convert our potentiometer data to a potentiometer packet that you saw before. So we will give it the packet. I will show you in the code later. And what it does is that it simply sets the data in the packet to the data that we have here. So you have to make sure about the size of the data. So in this case here, I know that each float is equal to 4 bytes. So I will first write the first data. I will first write the data at the first index of the buffer equal to the first angle here. Then for the next iteration, I will be at I is equal to 1, which means that I will skip 4 addresses because one float is equal to 4 addresses. And then I will write the next angle at this index, and then the third one and the fourth one, and I return the buffer. So this is the basic principle, but there could be some mixed types of data. For example, the servo data here, which can send a UNT8, a float, and a bool, and these will have different size of data. So you can see here that I first write at the buffer, I first write the channel, then I need to skip 1 byte because UNT8T is 1 byte. Then I write the angle here. The angle is a float, so it's equal to 4 bytes, which means that I need to skip 4 bytes. So 1 plus 4 is equal to 5. And then I write the success here, which is also 1 byte. So you just need to be sure about the size of the data if you plan on using this structure. Okay, so let's go back to this part of the code. So now you've defined your two types of structures. You have the data and the packet. So the packet is what will be actually sent on the bus, and the data is just a way to use the data in a more flexible way so that you can print it and do other things with it. Okay, so here you have your two structures. Now let's go inside of the loop function. So inside of the loop function, normally you should have something in the loop that reads the data from the sensor. So in my case, I have the get angles here. And the get angles, I think I've explained it in more details in the video for this particular sensor, but it will have a pointer of angles as an argument, which means that we will actually modify the pointer values so that we actually modify the values that the pointer is pointing to so that we can have the data later. So here we just compute the angles for the different channels. So this get angle here will modify the values to which this pointer is pointing for the 4 channels. So we have for channel 0, 1, 2, and 3. And it will also return the status here, which is equal to HAL OK if it is fine. So if this has executed with no issues, then it will be equal to HAL OK. In this case, we will get inside of this part of the code. Okay. So what we do first is we use the toArray function of the potentiometer packet so that we can convert the potentiometer data to a potentiometer packet. So this is the basic structure that you will be using throughout the whole code if you use these types of these two structures. Right, so it's very easy. You just have potentiometer.data dot toArray, and then you give it a pointer to UNT8T, and you give it the address of the packet. So this is really something that you can find in all of the other threads. So for example, if I go inside of the I don't know, let me go inside of another thread like the mass thread. So in the loop function here, you will see that the structure is very, very similar. If I can actually find the loop function. So the loop should be somewhere here. So here you can see, for example, we have the mass data dot toArray, then we give it unt8t star and the address of the mass packet. So it's exactly the same syntax throughout every thread. Okay, so once you've converted it to the potentiometer packet, then you have here a way to print what you are reading. So this monitor here is used to print the data inside of the serial terminal, just as I showed you before with the IMU here. So when I did the monitor enable, if you remember enable uh, or monitor enable IMU, it actually triggered this function so that it can print inside of the terminal. So this is what it did when I wrote the monitor enable. So this is just a way to print the data inside. Afterwards, we need to compute the packet ID. So this is, as I've said before, because the pod packet is defined as an identifiable packet. So inside of the protocol 23.h, I can't really see it here, but yeah, so inside of protocol 23.h, we defined the potentiometer packet as a reliable and identifiable packet, which contains here the CRC field and the ID of the sender. So here, this is what we do. We will compute first. We'll do the make identifiable pod packet. So this make identifiable will set the ID of the packet according to the ID that we set on the dip switch of the microcontroller. So I remind you again, but the dip switch is set here on the microcontroller. And if you remember from the video where I explained how the system was working, this make identifiable here uses the system get node ID function. And if you look through the get node ID function, it will return the node ID. And the node ID here was computed before by this function, the update node ID, which is called that at startup. And the update node ID just reads the data from the dip switch and returns the binary value. Like this is a binary value from the dip switch, and it returns a decimal value that it has computed. Right? So we can actually go from ID 0 to ID 15 because we have 4 dip switches. So now that we have called the make identifiable macro here, we will have computed the ID. Then we need to compute the CRC. So the CRC here is computed using the hardware CRC of the microcontroller. This is I might do a separate video just for that, so that you can have some more insight. But basically, on the STM32, we have what is called an hardware CRC. So I'll just show you what I mean. So if I go inside of the datasheet of the microcontroller, you see that if I type CRC, there is a CRC computation unit, which can be used to compute the cyclic redundancy check value. So there are two ways to do it. We can either compute it using the computation unit, but we can also compute it using another way. So as you can see, the make reliable my MCU macro is not inside of the protocol macro file, which is part of RoCo, but it is in telemetry, which is not part of RoCo. So why did I do this? This is because if you go in the protocol macro here, which also has make reliable, this one uses the function that is defined above, so this function here, to compute the CRC. So in the case of the microcontroller, if we do it in a software way, just like this, it will take a long time to compute, and it will actually make the communication maybe 2 or 3 times slower. So by using the computation unit, we can make it a lot faster. But I didn't put it inside of RoCo, the computation unit way, because then it is not cross-platform, which is what we want, as we will be porting this library to the Jetson, which runs Ubuntu, Linux, and is not on the same architecture as this microcontroller. So the make reliable function from the microcontroller is defined here in the telemetry function. The same can be said about the make identifiable function. It's not part of RoCo because it is very dependent on our microcontroller as it is set from the dip switch. Okay, So basically, we just use the make reliable function here um, to compute the CRC of our packet. Afterwards, we need to set the destination ID, so to which node we want to send it to. So right now, here I've defined in the telemetry.h the different nodes. So we have the Science 1 node, Science 2 node, HD, Nav, General node, and the Jetson. So if you don't remember which node is what, you can look at this graph here, and I've written the ID of each node. So the Jetson has the node 0, then the node 1 is the container, the node for the container. So this is outside of the rover, but underneath the mass container. Then we have the node of the PCB that is located near the drill. Afterwards, we have the navigation node, which is inside of the rover and has the IMU as well as the addressable LED strips. And we have the handling device node, which is near at the base of the robotic arm, and this one is interfaced with the voltmeter. So they all have their own unique ID here, and we can choose to which board we are sending the data. So in my case, and in most cases, you will be sending the data to the Jetson, which is why I set the ID to Jetson ID, which is equal to 0. Okay, so now that we have actually prepared the packets, we haven't sent anything right now. We've just prepared the packet. So then you need to send the data on the CAN bus. So what you can do here is just send the data through the network. So you just use the FDCAN1 network send pod packet and FDCAN2 network send pod packet. So you send the data on the two buses. So once you do this, you are actually done on the sending part of the of that of that microcontroller. So it is very easy to use. You just need, as a summary, to define the two packets here, and then you just compute, like set the data inside of the potentiometer data or whatever data you are using. You convert the data to a packet, and afterwards you send it on the network. So normally you shouldn't touch this part here because it has been written and it is working quite well. But if I had to give maybe some very small details, here you can see that we are creating a CAN driver, and then we create a CAN bus, and we will then give the CAN driver to the CAN bus, and this will give us a CAN network. So this is kind of the structure of RoCo, and it is very modular. So last year, for example, we didn't have the RoCan driver here, but we had an STM UART driver, which instead of using the CAN bus uses the UART, the UART protocol. And then what we did is, instead of creating a CAN bus here, we created a network bus. And then here, instead of doing this, we just did new network bus and we gave it the STM UART driver. So all of this to say that it is very modular, and it was just a choice to use the CAN bus this year, but the RoCo protocol can be interfaced with any type of communication protocol, and you just need to write the interface, which are the CAN bus or the network bus in this case, as well as the underlying driver, which could be RoCan driver, in our case on the microcontroller, or the CAN socket driver, which is running on the Jetson. Okay, so this was for the sending part of how to send data to the Jetson. Now let's talk a bit about how to receive data on this microcontroller. For example, if you are receiving an order, for example, to turn on a servo, or to rotate a servo, or to turn on some LEDs, like how do you actually receive data and how do you act on what you have received? So to do that, we have implemented a way to call functions. So if you go inside of the system, and so it's system here, then we'll go in source, and then in telemetry. So it's not here, this is RoCo. So system, then you have core, source, telemetry. You will see here a lot of functions which are called handles. So handles are basically callback functions which are called whenever we receive a packet on the CAN bus. So let's have a quick look at, for example, the servo packet. So here you can see that I've registered two handles, one on the FD1 CAN1 network and one on the FD CAN2 network. I then call the handle function, give it the type of packet, and then I inside of the parentheses here, I just give it a pointer to the function that we want. Okay, so it's very, very straightforward. And if you go, let's have a look first at the servo packets. So the servo packet is defined as the channel and the angle. So this is the channel on which the servo is connected, because we have 4 different channels, and the angle is the angle at which we want the servo to be in. And then the handle rotate here is defined in the servo thread, and then we can handle this function. So in order to create this function inside of a thread like this, we want to define it so that it does not belong to any object. So there are many ways to do this. You can either create a function outside of a class. This is what we do here with the handle ping function, which is the simplest handle. So the handle ping is defined here, and you can see that we simply send the date. We just make it reliable, make it identifiable, just like before, and we will send it back to the sender, so that we have some kind of ping. And so how do you actually define these functions? So if you go inside of the servo thread.h, you will see that it is defined as a static function. So servo thread.h here, and you can see that it is defined as a static function. So all of the handles have to be defined as static functions so that they can be called even if the object of a certain class does not exist. So this means that every servo threads, every object of the servo thread will have the same handle rotate. So this might be a disadvantage, but this is the only way that works right now. So every handle function has to be defined as follows. We have the name, of course, and then we'll have a first field, which is the sender ID. So the sender ID will be equal either to 1 or 2, depending on whether we are receiving the data on the FD-CAN1 or the FD-CAN2 buses. And then we have, of course, the definition of our packet so that we can receive the data. So if you look at the handle rotate function, you will see here that we have the sender ID and the packet. Then we can call this a macro here that I talked to you about before. So we check if the CRC is the same on the packet and on what we have calculated. If they are equal, then we can go to the next step. If they are not, then the packet is unreliable. Afterwards, there are some functions, so this is not important, but what you can see here is that we will send some kind of response to on the network. So here I've defined also a servo response packet, which is here filled by either success or false. I've also it also fills in the angle at which the servo has rotated to, and when it has gone through all of this code to check whether or not the package is correct, and at which angle the servo has rotated to, then it will send it back to the Jetson. Right? So in our case, if we have received it on the CAN1 bus, then we want to send it back on the CAN1 bus. And if it has been received on the FD-CAN2 bus, then we want to send it on the FD-CAN2 bus again as a response. So so this is the basic handling functions. So you just need, as I said, to define a static function or a function outside of a class with the following signature, and then you can do anything you want with the packet definition here that you send. So the thing that you have to know, of course, is that um, you have to write here the type of the packet that you are receiving. And from this point on, every ping packet that the microcontroller detects will call the handle ping function. So there is no like subscriber and publisher in the sense that we have a name for the packets, but the packets are defined by their type. So we can't have multiple ping packets right now, which call different handle functions. So all ping packets will call the same handle function. So this is our our limitations right now, but it is possible to register multiple callback functions to the same ping packet, so that when receiving a ping packet, it could call multiple handle functions. So this is possible also. Okay, so this is the basic gist of it on the microcontroller. So as I will now do a quick summary on how you can actually send and receive data in a very, very quick way. So let's say you have written a new thread. So for example, ADS potentiometer thread. So the first thing you want to do is to create these two structures here, potentiometer data and potentiometer packet. The data will be defined in the data structures, whereas the packet will be defined in the RoCo library as a protocol 23.h. Okay, so this is your first step. Then in the data structure here, you have to define the toArray function so that it can convert the data to a packet. So this is done by taking into account the type of data and how much data you have for your packet. You can optionally also write the toString function, which can be used for debugging purposes and can be displayed in the serial terminal later. So this is your first step. Then in the loop function, you need to first get the angles or get whatever data you want on the potentiometer data that you've defined here. So you just need to write a function that can do that. Then you need to convert the potentiometer data to a potentiometer packet using the toArray function. And afterwards, you can send it through the network with this structure here. So this is not enough for sending the data. You need, of course, to register the packet onto the RoCo library. So to do this, you go inside of the RoCo library here, and you will need to add the packet inside of the CAN bus folder here. So you need to define a new ID for the packet. Then you need to register it on the protocol register here as a new packet. And of course, it has to be defined. It has to be defined in the protocol 23.h here. So it has to be defined as a packet with the definition of what is what. So this is crucial. So these are the files that you need to modify. And I will show you once I am on the Jetson. You need to have the same library on both sides. So if you don't have the same ID defined in the protocol, then it won't work. So you need to make sure that all of the microcontrollers use the same version of the library. And to do this, I might just show you maybe an example right now. So, all right, so I will just show you maybe how to add a packet very quickly. So first, what I will be doing is go inside of the protocol 23.h, and I will create a new packet. So let me write, for example, a dummy packet. I don't know if I've already created one actually. So dummy. So no, there is no dummy packet. So let's write a reliable, identifiable packet, and I will call it a dummy packet. Okay. So inside of the dummy packet, I will just give it a simple unt 8t, and I will call it dummy data. Okay. So this is the first thing. Then I want to register this packet. So I will go inside of the protocol register here, and I can do register dummy packet. So now the packet has been registered. Yeah, so this is okay. Afterwards, I just go inside of the CAN bus and I can add my packet somewhere. So here in this case, I just do a defined dummy packet, and I will give it the ID, which is equal to 51, for example. So this is, I've decided to add it as 51. So here I'm almost at the limit, I think, of the number of packets that I can have. So if you go in the canvas.hpp, it's somewhere in include. It's not here actually. So CAN bus is inheriting from IO bus, and in iobus.cpp, I don't remember where the number of packets is defined, but it should be somewhere. Yeah, well, whatever. So this is not very important, but just tell me if you want to add more packets, but it's probably defined in iobus here, or in a message bus or somewhere. So yeah. So here you can see the number of packets that you can define. So it should be defined here by the definitions by ID, which is 64. And here this is 4 times 64. So if you want to add more IDs, you need to change these two values here. All right. So right now we are working with 64 different packets as a max value. So as I said, you need to go in the protocol register. So it was protocol register, and then you register a packet, and then in the canvas you just change, you just add the packet here and add its ID, which must be unique. So now this is it, and you've defined a new packet. So we can how do you actually share this library to your other devices? So first you will go on your workspace here, and what you want to do is first open a git bash terminal. You can do git status to see some changes, for example. So in my case, there are a few things that have changed, but not too much. Now I can go in git, and I just do cd, so change directory. I go in Orion firmware, then system and RoCo. And here, if I do a git status, you will see all of the things that have changed. So, for example, I've just added my packet here. I can just verify that it's building first. So let's build the project. Normally, it should build with no errors if I did things correctly. So here there are no errors, which is perfectly fine. And what I want to do now that I'm in the RoCo library is I need to add it to, I need to push it to the remote repository. So I just do git add, and I want to add these 3 files. So I don't want to add the build because if you remember the build, I modified it so that it could be used on this microcontroller. But if I want to share this to the Jetson, then I don't really want to add the build because then it will not be compatible with the Jetson, and I will need to comment, like I will need to change some of the lines again, because on the Jetson, I don't want to build with FDCAN, but I want to build with the socket driver. So I just do git add include something. I can do git add. So this was the protocol, then the protocol register, right? I just add it. And finally, the CAN bus. I mean, you could also just add everything and then change the build configuration on the Jetson, of course. That might be faster, actually. So I just do these three for now. Then I just do git commit m. So this is so you can add your text afterwards. So here I just write like added dummy packet for tutorial, and then I do enter. Afterwards, I just do git push. If I do git push, it will tell me an error, and this is normal. So this is the thing that you should look for. In my case, I want to push onto the branch, which is called by RoCo. So the branch that I want to push it to is this one, the RoCo branch. So what I will write is git push origin head dot l broco, and this will push my code. So I need to first write the password, of course. And here you will see that it has pushed the code to the remote repository. All right. So if I go in lbroco, you will see that it has correctly been pushed. But there's something to keep in mind. So now if I go in the hardware workspace, software workspace, you will see that in the Orion, so here I'm in master, if you see, you will see that if I go in Orion firmware, I go in system and Broco, the commit here is not the commit that we just pushed here. So this means that someone that clones the repository here will not get the last version of Broco if he clones it. Okay, so this is an old commit. This is 5015, and if you look at the history of the commits, this is not the last commit. So let's go in Broco, lbroco, and if you look at the history of the commits, you can see that the 5015 was the old commit that I did 2 weeks ago. So how do we actually like update this? So what we will do is we need to push the changes, the fact that we changed the commit. So you just go inside of the hardware workspace here, right? cd av workspace. And if I do git status, you can see here that it has detected that I am using a new commit with modified content. So I can just do git add, then I can just add this folder here, paste, and then I do git commit. Oops, git commit m, and I do just updated lib for tutorial, and I do git push. And now you will see, after writing my password, of course, that it has correctly updated the reference to my library. So if I go in software workspace, in the master branch in my case, and I go firmware, then system, Broco, you see that it has changed the commit to 13AE4FF, and this is equal to the latest commit that we had, where we just added the dummy packet for the tutorial, right? So this is it for this tutorial, really. And yeah, so I might so just tell me if you have any questions. But basically, now that you have updated the libraries like this, when you clone it, you can just do it just as I did in the getting started video. So you just need to clone the repository, then you do the git submodule update init remote, and this should update the library. So let's type this just to see. And here you can see that it did nothing because I already have the last version of Broco, and it will actually just update it to the commit that the repository here is pointing to. So because I just updated it so that it could use the latest version, then it will clone the last version of Broco. Right, so you just need to make sure to always push both the library to the correct repository, but also update the reference to the correct commit when you are working with this library. And this has to be done on both the Jetson and on the microcontroller. so that you can always keep the same library between the two and always have a working communication protocol. Okay, so I will have another video explaining in more details the communication side on the Jetson, and again, so it will be a bit easier to understand on the Jetson side.